Okay. So now we are at supervised learning. So supervised learning, as we know, it has like it's more like there's a teacher and a very small kid. You are teaching the kid like, hey, this is apple, this is banana, and these are all the things. Supervised training itself is divided into two parts for now,
Hmm.
but the core is same. Like you are teaching something to a machine, which is more like a very dumb machine initially, and then slowly you teach it something. So there are two categories for this. One is now we are going into, I would say, how to solve this problem. Basically, let's say you have a problem, like you are telling me, hey, like this Zoom video problem, like find where the human is and find the background pixels. Or another problem could be do the translation. Another problem could be, let's say, given a picture of a human, find the age of the human. So there are many problems. So we divide these problems into two parts for now. One is known as linear regression and another is known as logistic regression. So these two categories, one problem we solve for categorization. So let's go with the first. One is linear regression. It's more like, let's say I give you the picture of a human and I ask you what is the age of human. So it could be anything. It could be 49, it could be 50. So it's more like a continuous paradigm. Or what if I ask you like current stock price is this, what is going to be the stock price after time t? So that is also a linear regression problem where I ask you predict something which is more like a continuous. You will understand it better once we have the another category, which is the second category, which is like logistic regression.
Hmm.
Logistic regression is the category wise. So apple is one category, banana is one category, or I would say, let's say human is one category, animal is one category. In Zoom context, human body is one category, background pixel is another category. So once we have like a discrete kind of thing, like a category A or category B or category C, that is known as logistic regression, which is more like logical. Linear regression when it's more like a continuous paradigm. So one example on the bottom left is this. In the supervised model, let's say these you are giving model green apples and yellow pancakes, if you can
Hmm.
see it. So this is
Hmm.
the training data. You have
Hmm.
apples from different angles and pancakes from different angles. You train the machine to predict whatever it's coming in, and on the inference or in the test, when you deploy this model, you have unseen unlabeled data. That is the
Okay.
orange yellow cup coming, orange
Yeah.
cupcake coming. So when you give that to a model, it has to predict class is cupcake.
Hmm. Hmm.
So this is more like when you are predicting some class or category, some discrete thing, you call it logistic. And if on the right side, you are given these yellow dots, let's say,
Hmm. Hmm.
for each x is equal to 9, yellow, y is equal to 19, x is equal to 14, y is equal to 25. Can you see my mouse also?
Yeah. Yeah. I can see.
Okay, so these are the points which are given to you.
Hmm.
As you can see, there is a pattern here,
Hmm.
underlying pattern here. Like we used to do as a kids, like making some shapes,
Hmm.
stars or something like that. So there is an underlying pattern here. So what if I give you what about x is equal to 20? There isn't
Hmm.
any value there. So what you will
Hmm.
do is this is the value of y, 60.
Hmm.
So this is more like a linear, like for every value of x, you will give some value of y. This is more like
Hmm.
a linear regression. So this is an example of linear regression. This problem is an example of logistic regression. For this, the points where x is given, you also know the y. So
Hmm.
this is
Hmm.
supervised. For each x, you know what is y. For each x, you know what is y. For unknown x's, you predict what is the new y.
Hmm. Hmm. Got it.
And in this supervised, you know what is the input, you know what is the output category. So the only thing you need to understand here is one thing is more like discrete and one is more like linear.
Got it.
Now,
Yeah.
what you can do is, let's say I ask you like predict the weather tomorrow,
Hmm.
given all the factors like cloud conditions, weather, temperature. So you will use linear regression for that.
Got it.
If I ask you to make we are making an app where we need to actually know what kind of food a person is eating. That is more
Hmm.
like a category now. Pizza, it could be Italian, it could be Greek, or that is more like a logistic regression.
Got
So
it.
supervised training is broken into two now. If I ask you like predict the stock price in future, you will use something like linear regression.
Yeah.
And if I ask you what is the something in Amazon Go stores, they
Hmm.
actually want to recognize what the person is holding in his hand,
Hmm.
what
Hmm.
category of object is he's holding, and then they will say what is the price of that. Then you don't need to go to cashier. You can just pick up the thing and go out. Even in
Hmm.
self-driving, it's mostly about supervised. Is it a human? Is it a car? Is it something else? So these are more into uh, logistic regression category, and one is linear regression category. So you just need to, like, most of the industry is using supervised learning, and then you need to divide that problem. Then it becomes
Hmm.
easier for you to actually train the model with respect to that.
Hmm.
So these are the
So
two categories. Yeah.
if we take the example of Uber, Ola, or Oyo, so
Uh-huh.
where this comes into picture?
If you take into example of Uber, Ola, Oyo, that is still a linear regression. They want to predict the price or the time it will take from riding from point A to point B, given the previous data and the new data, new conditions.
Hmm. Hmm.
That is still a linear kind of a model. A continuous value you will predict. You will not predict that person will reach or not reach. You will
Hmm.
predict how much time it will gonna take to reach. So there isn't any
Yeah.
discrete category. It's still a continuous category.
Okay.
So that is more like a linear regression model now.
Got it.
So let's go ahead. So, so all these linear, be it logistic, all of them actually, what you are doing is, if you see this example,
Hmm.
what we will do is we will go with the linear regression because it's very easy to actually understand.
Hmm.
So if you look at this function, y and x
Hmm.
is more like a cubic function. If you
Hmm.
know, like, I would say like ax cube plus bx square plus c. Y,
Hmm.
if you predict y is equal to ax cube plus bx square plus c,
Hmm.
that is more like a cubic function. So if you have that cubic function, you need to find the value of a, b, and c,
Hmm.
and that will purely fit this function.
Hmm.
So basically, what you are doing is in machine learning, everything what you are doing is you are trying to find a function which will fit this curve.
Hmm. Hmm.
Basically, you have something like a cubic function, it's somewhere here. What you are trying to do is you are trying to like fit it somehow that it exactly matches this and it has the minimum error. What you want is
Hmm.
some nice fitting function. That's what you are doing. You are giving
Got it.
some training data and you are fitting a curve on this training data. This is ML is. That's it.
Hmm.
There isn't anything more and there isn't anything less. Then it becomes more like ops and all those kind of extra things where you need generalization and all those things. But in the core, it's just like fitting some curve on given training data. If you are
Hmm.
able to do that, you can do whatever you want. In this example, let's say these yellow things are some data and y is the temperature that day.
Hmm. Hmm.
So you have now a nice curve. So even whatever the x is given, let's say x is given 35. For that, you don't have the yellow dot, but you can still predict what would the value gonna be because you have the nice fitting curve. So this is what you are doing in ML. You're just fitting a curve to points. And then once you have that fitting curve, then you predict whatever the value based on that function, what you have fitting.
Hmm.
So now we'll learn like how to do that and what's the approach used to do that.
Hmm.
So what we do is we make a hypothesis, very simple hypothesis. Like in the previous example,
Hmm.
the input was x. Let's say instead of x, you have two inputs. There could be multiple features to your model.
Hmm.
One could be temperature, one could be heart rate, or something like that.
Hmm.
Let's say I wanna predict what's gonna be height of your son
Hmm.
when he's 20 years old. So I can take input father height and mother height. So
Hmm.
let's say x1 is father's height, x2 is mother's height. And I
Hmm.
want to predict what is going to be your son's height in future when he is mature. So basically, I form a function, very simple function, fx is equal to x1, comma x2, w1 x1 plus w2 x2. My hypothesis is it's going to be some simple function like that.
Hmm.
So basically, I will input your height. X1 is your father's height. X2 is the son's mother's
In
height.
mother side. Hmm.
Mother's height. Then my value is gonna be W1 X1 plus W2 X2. Whatever. Let's
Hmm.
say X1 is 5, X2 is 4.
Hmm.
So 5 W1 plus 4 W2.
Yeah.
So if you know the value of W1, W2, you are done.
Hmm.
Your job is basically to find these two variables, W1 and W2. If you find the value of W1, W2, you are done for the day, and you have a perfectly good model fx, which is going to be, let's say the W1, W2. Let's say God comes to your dream and he says W1 is 1 and W2 is, let's say W1 is 2 and W1 is, okay, let's say W1 is 1, W2 is 2. Gods
Hmm.
come into your dream and the function becomes x1 plus 2x2.
Hmm.
You fill in father's and mother height, you are done for the day. You know what is going to be the predicted son's health. So
Hmm.
thing is, where do we get this help from God? Who is going to give you the value of W1 and W2?
Hmm.
That is the major ask, or that is the task which most of the, when we say we are training a model,
Hmm.
people say, hey, it's taking 1 week to train a model. What they're doing is basically finding the value of W1, W2.
Hmm.
If the God comes and then he will just tell you the value, but we don't have God right now. So our model needs to learn it with our learning algorithms. What is the actual value of W1, W2?
Hmm.
Okay. So now we are clear that basically what we do in machine learning is we make a hypothesis that we have a function with two variables and two input data features, which is mother's height and father's height. We need to find W and W2. That is clear for you. Okay.
Yeah, yeah, correct.
What we do as a mathematicians is we'll make a cost function, or some people call it also a loss function.
Hmm.
And basically what they are going to do is they are going to minimize that cost or loss function. So
Hmm.
what I'm talking about. So what is going to happen is, okay, these are not actually good. Okay. So, okay. I wish I would had a whiteboard. I can just draw it, but let's do it hypothetically. So let's say, now you have 5 samples, like 5 training samples. Training sample 1, I'm gonna call it, so G is the ground truth, or maybe we call it training sample 1. Okay. So what we are doing is we are making this function into a cost function. So what
Hmm.
happens is, for each input values, let's say we have example of, you have 5 neighbors. They all
Hmm.
have sons 25 years old. We take their examples. We can randomly put W1, W2 be anything. Let's say the God told us it's 1 comma 2, but
Hmm.
as we don't have God, you use random number initializer. You put 3 comma 4.
Hmm.
If you put 3 comma 4, the value that you expect is going to be very different from value which is actually is.
Hmm.
So there is going to be huge gap. So what are you going to do is you are going to randomly try different W's.
Hmm.
Let's say W is 3 comma 4, let's say 5 comma 6, or 7 comma 8, or 100 comma 200. So you are randomly trying different W's, and what are you finding is some error in height, that your, let's say, predicted height, because this is a function, whatever it's going to do, it's a prediction. Let's say your x1 is 1, x1 is also 1, and x2 is 1, x2 is 2, and W, so your height of your son is, let's say, 5.
Hmm.
Your height is 1 unit, your wife's height is 2 unit. God told you that W1 should be 1, W2 should be 2.
Hmm.
So your son's height is, let's say, 5.
Hmm.
So if you do the multiplication, so 1 multiply 1 plus 2 multiply 2.
Hmm.
So if we knew the value of W1, W2, the height is coming to be correct, because
Hmm.
God told you, and you also know your son's height is 5 unit. But let's say now W1, which you randomly initialize to be 3,
Hmm.
and W2, which you randomly initialize to be 6.
Hmm.
And now if you use this function to evaluate the new height of your son, it's gonna be 3 comma 3 multiply 1 plus 6
15. It
multiply,
will be 15. Yeah.
yeah, it's gonna be 15. But you know your son's height is 5. So there is a huge gap. And similarly for 5 of your neighbors, there is still a huge gap. Let's us try some other value. Let us try, instead of 3 comma 6, let us try 2 comma 4.
Hmm.
If I use 2 comma 4, your son's height is 1, or your height is 1, your wife height is 2. So 2
10.
multiply 1 plus 2 multiply 2. It's 6.
No, 6, yeah.
Prior height was 15.
Hmm.
Now it is 6. Actual height is 5. So this is closer to what the God is expecting or what the universal value should be. So you are getting it.
Yeah, yeah.
Just by randomly trying some values, you are getting closer to what it should be. Or let's say I'm not that lucky. I try 8. I try 8,8.
Hmm.
Now height becomes 8 plus 8 to 16,
24.
24. This is not good direction. You're getting it.
Yeah,
If we are
yeah.
increasing the values, the error is increasing.
Hmm.
If we are decreasing the values, error is decreasing. So you have to somehow, you are getting the direction. You are knowing the concept of direction. Okay, if
Hmm.
I increase the W's, the error is going up. If I decrease the W's, somehow the error is decreasing.
Hmm.
So this is the concept of gradient descent,
Hmm.
or finding the direction where should we move.
Hmm.
This is how you learn W's. What you do
Hmm.
is you have some initially randomly get some values,
Hmm.
find the using those values, you find the
Hmm.
height of your predicted height of your son. You
Hmm.
find the error. There's a huge gap. Now what you do is you need to change this W1, W2. You change them in a way so that they go close to your son's height. So now
Hmm.
what we are doing is instead of 3,6, we are going for 2,4. Now then we'll go to 1,2. So this is how we are going to decrease the W's. So to
Hmm.
find this direction, we call it this algorithm, the gradient descent algorithm.
Hmm.
It's very easy, but I don't have a good example. So this is the cost function. What we do is we get the ground truth, which is g
Hmm.
of x, your son's height. Y is your son's predicted height based on this
Hmm.
function, the W1, W2. What is the cost? The difference between these two.
Hmm.
Average this cost across your neighbors and say, hey, we have a huge error. This is
Hmm.
W is a huge error. W,
Hmm.
why we are saying W? This is a function of W, because of W there is a loss. So we are saying there is a huge error. We have to decrease it. So
Hmm.
you reduce this cost function. So if you have done the primary mathematics in school, like I would say like +1, +2 in non-math, they teach very primary mathematics, how to find the minima of a function. So if I say this is the function which is composed of W1, W2,
Hmm.
the cost. So this is a function. You need to minimize this function. This is, if you minimize this function to 0, that is
Hmm.
what you need.
Hmm. Hmm. Hmm.
So if you minimize this function, this is what you need at the end. Okay.
Hmm.
So let's say your function has a nice ball curve, which doesn't
Hmm.
happen most of the time. Let's say it has a nice curve like this. So what you do is, let's say with some random W's, you are somewhere here. You
Hmm.
need to go somewhere here, which is the minimum of this function.
Hmm.
You find the gradient descent. How do you do that? There is a very nice example. Let's say you are on a mountain.
Hmm.
I have like blindfolded you.
Hmm.
Okay. This is a mountain or a valley, something like a valley. You are on some place in the valley. I put some blindfold on your head. You cannot see anything. You only can use your feet. I ask you to go to the bottom of the valley. How would you
Hmm.
do that? Basically, you will take your feet and wherever the gravity is taking you, or you will check the direction of the height. You will say like, hey, if I go to this direction, I'm moving up. But if I go to this direction, I'm moving down. So you will just follow this direction and at the end, you will reach the bottom of the valley.
Hmm.
So this is what gradient descent does. It's a very
Hmm.
simple convex function. If it's a convex function, it's very easy. If it's a not convex, let's not go into that details. But basically what you are doing is going to the bottom of a function, of a loss function. Once you minimize the loss function, whatever the W1, W2 you have, you're just going to give that values and assume that these are the values of my model. This is what a
Hmm.
model training is. Basically, a human who is traversing around this valley and going to the bottom. Once you go
So
to the bottom,
I
yeah,
have a question here. So finally, that W1, W2 will be constant values. We just
yeah,
need to
those,
find.
yeah,
Yeah.
yeah, yeah. So at the end, what you have is this function, this A function.
Hmm.
And this is what all the models are, just
Hmm.
W1 and W2s. And X1, X2 is customer input data.
Got it. Yeah.
So let's say there could be example like predict the future stock price.
Hmm.
In that X1, X2 could be PE ratios and all those kind of things. And there could be x3, which is time t. T is also a feature now. So basically you have compressed everything to a function, find the minima of that function, and that is your final model.
Yeah,
Same
got
thing
it.
occurs for regression. Same thing happens for logistic regression. So in this Zoom example, what they had is Zoom initially had a lot of images of people sitting in front of cameras. And then they marked all the pixels which are non-humans. And then they marked all the pixels which are humans. And then they used a function fx, which is actually your model. And you asked the machine to learn a model, those weights, such that to minimize that function. It minimized that function and it found a model. Now this learned model is just weights. It's just matrices or vectors. And then you put that into your machine. Basically, when you're downloading a model, you're just downloading some weights. These W1, W2, we call it weights, or you can call it matrices or functions. This is what you download, and you use that to predict some new value. So in this case, basically, let's say these x1, x2 are just the x and y values of each pixel here in this screen. Okay, these are the just RGB values of each pixel, and the model is predicting whether this is human or background. Okay, now they have learned W1, W2, they can use that. So what they will do is basically in a logistic regression case, they will say is like, if x1, x2, let's say these are RGB values, basically what it will do is x1 W1 plus x2 W2, if it is positive, then this is human. If these come out to be negative, then this is the background. This is what they're doing. That's it. You just have some weight function. So each weight function is multiplying each pixel with this weight function and then finding whether it's a human or background. This is what they're doing for apple and banana, for anything human or non-human, finding red light or yellow light. So even translation or non, like from going from English to Hindi, everything, this is what they're doing, just finding the weights and finding the minima. So if somebody wants to train these functions, everything has been implemented in TensorFlow or PyTorch. Most of the people should use PyTorch now because that is, I would say, much easier to use. So everything of this is implemented. You just need to make a data pipeline and a cost function. Decide the cost function, not even write the cost function. Just decide whether this is a regression problem or a logistic regression problem or a basically category problem or category problem or a continuous problem. If you decide that, give the data, give the output, the model is itself going to train. It's going to take 7 days or more than 7 days, sometimes even months. For the Google translation model, it takes them months to train that model. Once you have trained that model, just save those weights. Whoever have those weights, they are going to get the correct results. So now I can give you some examples, but they are not that interesting.
So one question here. So with respect to height prediction, is it a logistic regression or continuous or discrete?
It's a continuous problem. Your son's height could be 4.5. It could be 4.7. It could be 4.77779. It could be even that kind of number. So it's more like a continuous. It's not category.
But I'm confused, right? So you are only getting height, right? And it's specific to a single person, right? So I'm not convinced that it's a continuous.
So you are not convinced that it's a continuous function.
That's what I'm. Yeah, correct.
Yeah. So basically, you have to understand what is a category and what is a continuous. So if the question was, is your son's height gonna be larger than 5 foot or lesser than 5 foot? These are two categories. But I'm not asking that. I'm asking what is the height of your son is. So that could be 5.5. That could be 4.1. That could be 4. That could be 3. That could be 21.
No. That I understand it will be continuous. Given today's height, what will be his height after 5 years, after 10 years, after 15 years? Then it is a continuous problem, right? But if I'm asking what will be the maximum height given my wife's and my height, and if I'm trying to predict his height, right?
Yeah, when he's 25 years old, when he's mature. Yeah. I think what you are confusing is, what you are thinking is that his height is gonna be some fixed number. It's not continuous number, it's a fixed number. So why are you saying that this is gonna be a continuous number? I think this is what your doubt is. So that fixed number itself is not a category. It's some number. If I ask you, like, is is your son height gonna be larger than 5 foot or lesser than 5 foot? Then there are two categories. Category 1, lesser than; category 2, greater than.
Greater than, yeah.
Yeah, that is category. But what I'm asking is exact height of your son. That is a real number. Let's say you want to save that into your computer. You won't save it, you will save it as a float number. You want to save it as an integer. Okay, so that is a continuous number. His height is gonna be fixed, something fixed, but it's his height. But let's say another person comes, his height is gonna be 4.65 or something like that. So the domain is continuous. For each person, the domain, it could be anything. It could be from 0 to 100 or anything, like anything.
Got it, yeah.
The output domain is float. It's not category. But if I ask, like, hey Durga, is it gonna be lesser than 5 foot or greater than 5 foot? If we just want to predict that, then you are gonna use a bool. You are not gonna use a float for that. You are gonna assume that bool value 0 is less than 5 feet and bool value 1 is greater than 5 feet. So then it becomes
I think I got it. So I'm only thinking from one person perspective. If I think from all neighbors and all,
then the domain is a continuous.
And the x-axis will be means the male's height.
Let's say take this example. This is, let's say your son's height only depends on your height, which is x, and this is what is the son's height. So these are the examples. Let's say your height is 40 and your son's height is 60 now. So there could be another person whose height is 41 and his son's height is gonna be 62 something. This is a continuous domain.
Got it. Yeah, I got it.
You should go through this view. But if you can see that this cannot happen in real life, like it's very hard to actually predict height just from mothers and father. Like you could have two sons, both will have different height.
Correct.
That the feature engineering part comes. Like you have to include features which are more dense and which have more information. You will input your height, your wife's height, your son's genetics, some kind of genetic information, and your son's eating habits, and all those kind of things. Only then you can predict the proper height. Otherwise, it's gonna be a rough estimation.
Correct. Yeah.
That's why it's hard to actually make machine learning models. But once you have a really good data, which has all the variations, then you can predict very nice features in output and very nice output of your son's or daughter's height. So basically, just get a data, make a cost function, whether it's a linear regression or logistic category or linear. Just do that. Next time I'll give you very simple examples of age prediction. Given the photo of a person, predict his age. That is also a linear problem. Like every person will have different. The domain is linear, and then we will do a simple example of a very simple basic MNIST. Like given the OCR, like this example, like actually, like OCR is something like that. So they will write something, and you have to predict what they are writing. So this drawing is A, this is B, this is A, this is N. Now this is a logistic category problem. Given I find the category, whether it's A, whether it's B, whether it's C, whether it's D. Okay, this is more like a category problem. So this OCR is very important problem in ML. We will do very basic ML problem coming from OCR, and this is also OCR problem. Corrosion detection. Detect where the corrosion is happening. So if you can see down on the bottom, you can see where the corrosion is happening. It's marked by green pixels. So for each pixel, you need to find whether this has corrosion or no corrosion. So this is a category, no category. Green means there is corrosion, no green means no corrosion. So for each pixel, you are predicting whether there is a corrosion or no corrosion. So what you will do in future is you will collect data like this image 1, image 2, image 3. You will ask humans to mark the pixels which have corrosion. Okay. Or each pixel which have corrosion. You will train the model and then ask the model to do the same.
Got it.
And same thing is happening with Zoom call. Like this is your background and this is human. Okay, let's say assume human is corrosion and background is no corrosion. This is also two categories now. So similar thing is happening here. So the good thing about deep learning, which most of the people are like going is more like a buzzword now, is like you don't need to model your model. Like you don't need to learn what is inside the model. You can just treat it as a black box and ask it to give you something. It will do everything. Uh, so these are like you can have more than two categories. You can have green minor corrosion, red moderate corrosion, blue severe corrosion. So fourth category is no corrosion. So you can have all those categories. Some people are using this for pipeline monitoring, like where the pipeline is getting corrosion or no corrosion. So like there are a lot of AI applications. Anomaly, no anomaly, predictive maintenance, improving operational efficiency. So this is a very small example of convolutional neural nets, which I will cover tomorrow. This is basically giving you what is happening inside. When you say model, this is your model. This whole thing is your model. Input is some image and output is something, let's say two variables. This is just, let's assume this is just giving whether a male or female image, two categories, whether it's a male of image or a female
Female
image.
image, yeah.
Okay. And these, if you see like these are roughly they call it neurons or something like that. It's roughly taken from model of the brain. Like these are the neurons connecting different parts of the brains, and then you are taking some decision. So this whole part, you can just code it in PyTorch in 2-3 lines. You just need to make a data pipeline.
Yeah, this is irritating, right? Yeah, I know. Yeah, go ahead. Yeah.
I think, yeah, okay. So basically, this is your model, and once you have this model trained, you are just gonna use this model weights and redo this. Basically, whenever a new Twitter image comes, you're gonna input the image, and this is model is gonna give you two outputs, whether it's a male or a female. Okay. This is known as convolutional neural nets. These are, you can say this is just buzzwords for now, but this is already implemented for you. Like whole thing is packaged for you, so you don't have to worry much. This is a very basic example of this is 1991 research. They use this on your postcards or all your post emails. People used to write the pin code. And basically they will write 0, 1, 2, 3, and this is how they used to detect where this letter is posted. And this was happening in 90s by Professor Janlikan from New York University. And he's now head of AI at FB, Meta, Facebook. So if you can see like above, you're getting answers like 9, 0, 1, 2. So given this image, it's detecting category. What category of numeral it is going from 0 to 9. There are 10 categories now. Okay. If you can see, this is also noise resistant. See, even if you put noise on 4, it's still the answer is 4. So that is more like generalization and how to make it better. So that actually then you divulge into two domains. Are you going for NLP kind of domain or computer vision kind of domain? Then people basically what they are doing is they are learning things to make it better. So they will put noise, they will collect data from very noisy images so that your model generalizes well. These are the current networks which are used. If you see similar structure, people actually get confused by reading these networks. You don't need to know anything about this network. Everything here is given for you. You just need to make a data pipeline, make a better cost function, add some generalization capability, and just train the model for 7 days. You will get really good results. There are now array of architectures. Like each lab is like giving some new words or new models. They're just changing some things in the model, like one connection to another, and they're calling it a new network. The good thing is, if you are using PyTorch, it has all the implementation inside it. Just use the raw PyTorch. Like, but the most favorable network to do anything right now is ResNet, residual networks. You don't need to learn anything about it, just use ResNet. This is like basically how the OCR is being done. Basically,
So
first it detects where the box is.
what is the use case for which we can use ResNet?
So anything you can use ResNet to do logistic linear regression, logistic regression, OCR, NLP, anything. Like what is happening is basically they are finding that all the models like brain is capable of doing NLP, CV, research, anything. You can ask brain to do anything, it will learn everything. So similar, these deep learning models are capable of doing anything. You just need
Got
to
it.
give input and output, train it, it's gonna do everything for you. So if you see this is doing OCR, like the live OCR, which Google has in its camera, and even companies like AWS and other companies provide. So basically, let's solve this problem very easily. Like what you are gonna do. So what you are gonna do is, first you are gonna detect where the text is. We are gonna divide this problem into two parts: where the text is and what the text is. So to find where the text is, basically I'm gonna find where the text is. Let's call it bounding box model. Basically, it detects where the object is. Even this is used in self-driving cars, where the human is, where the car is, where the bicycle is, where it is. To find where it is, it's also a linear problem because you don't know what the x and y is. X and y is a linear domain. Basically, if you find one x and y and the bottom x and y, and you make a box. So basically,
Got it.
you are taking a model to find where the x and y is of this Abbey. It will give you this x and y and this x and y. Okay. Once you have that, you make the box. Once you have the box, now it's a category finding problem. A, B, B, E, Y. So you're getting to model any complex problem like OCR, you can just divide it into first linear problem and then a category problem. You just do a linear model separately and then a category model separately. Combine them, you have OCR engine, which is costing people millions of dollars, and it's very cheap to make it on your own. Okay, then you can use it anywhere. And this is how they are. It's very easy actually. And you can also use like Google Vision API, Amazon Recognition, or Microsoft Azure Computer Vision Library, and they're going to charge you for each prediction. Yeah. So yeah, I think these are the only slides I have right now.
Okay,
Yeah.
got it. Yeah.
But I think this is more like a brief overview of what ML is. Like if you just divide into two categories, solve each category using some cost function. Let's do examples one by one tomorrow, and then I think we can go deep.
Sure.
It's still, I think the one thing we should know, it's still not pure science. It's more like an art. Nobody knows like what is the best way to do it. You just need to try a lot of things, and whichever is the best, just claim this is the best model. So this is how the industry is working right now. We don't know what is happening, but we know like it's working. So that's it. There isn't any foolproof theory like how to do like non-convex optimization. There isn't any much theory about it. It's more like a practical thing. You just train it. It will give you some results. Just compare 2-3 models, whichever is the best, ship it. And in the production, what you do is continue updating it. Continue updation means like get more training data, update the W1, W2. This is what is. Yeah. So I think this is it. I think that's good enough for today.
Yeah, let me stop recording.